Pryluky, Ukraine, November 1991. 3 in the morning. A lieutenant colonel sits in the left-hand pilot's seat and stares into the darkness beyond the cockpit glass. Outside, it's cold and damp. The air smells of the steppe and of jet fuel. The aircraft is standing still. It's going nowhere. But the man is not asleep. Beneath him sit 326,000 pounds of fuel, 148 tons. A full load. And a full load isn't given every day. The landing gear works at its limit, and the concrete of the apron isn't made of rubber either. But tonight, it's full. Behind his back, in a bay, hang training cruise missiles. To one side is a switch he hasn't once touched in earnest in 10 years of service, and most likely never will. Most likely. He isn't thinking about nuclear weapons. He's thinking that the flight is at 6 in the morning again, and that the galley has run out of instant coffee. Here's the question worth asking at the very start. Not a technical one, a human one. What happens to a man who spends 15 hours inside a machine capable of destroying a city? Not in the sense of the psychology of war, that's a separate conversation. In the plainest possible sense, how does he eat, sleep, manage the toilet, talk to his crewmates, keep his reactions sharp in the 12th hour of a flight over the Atlantic? The Tu-160 is called the most comfortable strategic bomber in the world. That's true, but it's only part of the truth. Because comfortable here doesn't mean what you think. First, some scale. Without it, none of this makes sense. The Tu-160 isn't simply a large aircraft. It's the heaviest combat aircraft in the history of aviation. Maximum takeoff weight? 606,000 pounds, 275 tons. For comparison, a Boeing 747 at full load weighs around 800,000 pounds, but it carries 300 passengers with their baggage. The Tu-160 carries 4 men and weapons. 4 men. And 600,000 pounds of machine around them. Wingspan swept in, 115 feet. Swept out, 180. Fuselage length, 177 feet. Roughly a 5-story building laid on its side. 4 NK-32 engines produce a combined thrust on afterburner of around 220,000 pounds, more than any other combat aircraft in the world. The turboprop Tu-95, with its 4 NK-12s, belongs to another era, another kind of physics. Top speed? Mach 2.2, about 1,380 miles per hour. Service ceiling, 52,000 feet. At that altitude, the sky darkens to deep blue, almost ink black near the horizon. And all of it for 4 men who must not lose their minds over 15 hours. It seems a trifle now. It's not a trifle. When the Tu-160 was being designed in the late 1970s, the ergonomics of the cockpit and the living conditions of the crew were not the first priority. First came speed, then range, then payload. Then the problem of packing all of it into a single airframe without tearing it apart at supersonic speed. People came later, as usual. But then something important became clear. None of those parameters mean anything if 8 hours into the flight, the crew starts making wrong decisions out of fatigue, hunger, or the plain need for a toilet. It sounds crude, But that, in the end, is essentially how the engineers at the Tupolev Design Bureau framed the problem. Not in the official documents, of course. There, the words were different. But the meaning was exactly that. We'll return to what they did, and to what, in the end, they couldn't do. Now, about the predecessor. Because without the Tu-160, the story of the Tu-160 doesn't hold together. The Tu-160, Bear, as NATO called it, first flew in 1956 and flies to this day. That alone is remarkable. A turboprop strategic bomber in an age when everything around it had long gone jet. But that's not the point. The point is what it was like to fly the Tu-160. 4 NK-12 engines with contra-rotating propellers produced a noise from which, in the words of flight engineers, your brain started to vibrate after about 3 hours. Not a metaphor. Literally, the noise level in the Tu-160 cockpit exceeded every permitted limit. The crew worked in headsets that pressed on the skull, and by the end of a long flight, their ears physically ached from pressure and noise at once. The toilet on the Tu-160. There's a subject the official histories of aviation prefer not to touch. A pity. On the early versions, it was, to put it gently, not a restroom. A bucket with a lid. An exaggeration, but not by much. Later, it improved into something you could call a lavatory at a stretch. But either way, to use the toilet on the Tu-160, you had to unbuckle your harness, disconnect the tether of the survival kit, and squeeze through a narrow passage. With a parachute on your back that never came off, it's set into the seat pan itself, and nobody removes it in flight. On a strategic bomber, over the ocean, in an oxygen mask, if the altitude called for one, pilots joked, "The best way to lose weight is to sign up for long-range aviation." And into this context, a world of roaring propellers, tight passages, and institutional discomfort, comes the Tu-160. At first, it seems like science fiction, then like a mockery of common sense. Because in a country where there are lines for sausage in the shops, someone is seriously debating what the upholstery on the pilot's seat of a strategic bomber should be. Yes, exactly that. At one technical meeting in the late 1970s, reconstructed here from indirect sources, the exact minutes are unknown, the quality of materials in the crew rest area was, among other things, discussed. Leather panels, adjustable lighting, fold-down sleeping berths on a strategic bomber. Funny? Wait, it's not funny yet. It gets funny later, when it turns out how much all of this cost and what the crews actually thought of it. The global question of this series, here it is in its plainest form. Is the Tu-160 a monument to engineering genius, or a monument to a system that spent money as if it were being printed in the shop next door? Or, and here it gets more complicated, are those the same thing? There'll be no answer now. It comes later, when we've gone the whole road, from the drawing boards of the Tupolev Bureau to a hangar in Pryluky in November 1991, where a lieutenant colonel sits in the cockpit and thinks about instant coffee. For now, just hold the question in your head. Next, the world before. How men flew on what came before the White Swan, and why the people who lived through it looked at the Tu-160 as if they were seeing an alien ship.
There's a phrase the veterans of long-range aviation like to repeat. After the Tu-160, any aircraft feels quiet. It sounds like an exaggeration. It isn't. The noise level in the Tu-160 cockpit at cruise is around 100 decibels. For comparison, a loud rock concert is about the same. Only the concert lasts 2 hours. A flight on the Tu-160 lasts 10 to 16, and there's nowhere to go. The airmen wore special aviation headsets that pressed foam cups against the ears. By the 8th hour, the head hummed from the inside. By the 12th, men stopped talking unless it was absolutely necessary. Not because there was nothing to say, but because they heard each other poorly, and nobody wanted to shout more than needed. This is worth fixing in mind, because this is the backdrop against which the Tu-160 will appear. 1955. The Soviet Union understands that it has nuclear weapons and no reliable way to deliver them to United States territory. Intercontinental missiles aren't ready. Submarines exist, but not in the required numbers. That leaves aviation. It's then that the decision is taken. A strategic bomber is needed. One able to reach North America, do its work, and return. Officially, return. Planning documents mention landings at Arctic staging airfields, and later, Cuba, allies. But in the smoking rooms, over a drink, the question, "And how does it fly back?" sounded different. There, it was answered honestly. Not always did they know. Here's where people usually go wrong. They assume Soviet strategic aviation was built out of strength, out of confidence in victory. In fact, it was built out of fear, out of an understanding of its own vulnerability, out of the fact that the Americans already had the B-52, while the other side had only the turboprop Tu-95, which in theory, American interceptors could run down without much trouble. Fear is a good engine of progress. Expensive, but good. The Tu-95 first flew in 1956, a year after the first flight of the American B-52. Both aircraft survived into the 21st century. That, perhaps, is the only thing they have in common. The B-52 is a jet, 8 engines. You couldn't call it quiet either. Early B-52 crews lost their hearing no less than their Soviet counterparts. The high-frequency whine of the turbines wore them down in its own way. But the character of the noise was different, not the low-frequency vibration that came from the NK-12 propellers. The Tu-95 is a turboprop, 4 NK-12 engines with contra-rotating 8-blade propellers. Soviet engineering chose this path deliberately. At the same thrust, a turboprop burns less fuel than a jet at cruise. Greater range. The logic is iron. Only the side effect of that logic is that very roar from which the internal organs vibrated, literally. At certain settings, the rotation frequency of the enormous propellers entered resonance with the frequencies of the human body. Airmen described it in different ways. The stomach started to vibrate. The liver felt like it wasn't mine. An inexplicable anxiety from the inside for no reason. This was neither metaphor nor mere fatigue. It was physics, infrasound, which the body feels but the ear doesn't hear. The genetics of fear, literally at the physiological level. One flight engineer who flew the Tu-95MS in the 1980s recalled, paraphrased, not verbatim, that after an especially long flight, he couldn't speak normally for several days. Not because his voice was gone, because he'd forgotten how to speak quietly. Inside, everything still hummed, and it seemed he had to shout to be heard. In the late 1960s, the Americans began developing the B-1, a supersonic bomber with variable geometry wings, hard to detect at low altitude, a fundamentally different machine. Soviet intelligence reported it as best it could, that is, late and imprecisely, but broadly correctly. And the system's reaction was predictable. We must do better. Not, we must make a response, precisely better, faster, farther, heavier. This was the Soviet logic of the arms race in concentrated form, not to seek an asymmetric answer, but to strike symmetrically with a surplus. The assignment for a new strategic missile carrier appeared in the early 1970s. It contained everything the Tupolev engineers would later call, off the record, gently put, the wish list of a man who had never worked in aviation. Speed, over 1,250 miles per hour. Range, around 7,500 miles, 12,000 kilometers, without refueling at standard load. The figures in the specification were more ambitious still, but the real practical range came out at exactly that. Payload, up to 99,000 pounds, 45 tons. Takeoff weight, in the region of 606,000 pounds. And a crew of 4, who must control all of it. It doesn't look important now. It becomes so later. At the Tupolev Bureau, the assignment was not received as a gift. One participant in the design recalled later that when the main parameters were read out at a meeting, the room fell silent. A long silence. Then someone, not the chief designer, one of the rank and file, said quietly, "This isn't an aircraft. This is science fiction." Nobody answered him, because technically he was right. To build an aircraft that weighs 600,000 pounds and flies faster than twice the speed of sound is one task. Very hard, but comprehensible to engineers. There's aerodynamics, there's metallurgy, there's thermodynamics. But to make it so 4 men inside that machine could work for 15 hours straight, not simply sit, but work, make decisions, react to emergencies. That was a task for which the engineers of the early 1970s had no ready answer, because nobody had done anything like it before. For the B-1A, the Americans designed a jettisonable escape capsule for the entire crew. Soviet designers studied that assembly with particular attention. Elegant, but expensive and heavy. The Soviet Tu-160 would go another way. Individual K-36DM ejection seats. More on that later. That decision would come back around, but not the way anyone expected. Separately, about the look of the white Swan and why it's white. The competition in the early 1970s was won by the Myasishchev Bureau with its M18 project and the Sukhoi Bureau with the T-4MS. Tupolev considered a supersonic giant a gamble, but the order went to him. The production base, the experience with heavy series aircraft. The Myasishchev groundwork was taken as the basis. That's how the silhouette came to be. And the white color isn't aesthetics. It's a radiation-resistant coating. Protection of the airframe from the light flash of a nuclear blast. Without it, the metal would warp at the flash from the instantaneous thermal shock. Beauty is a side effect of the physics of survival. They held out. But that doesn't mean everything was fine. Next, the specification itself. Point by point. With a comment after each,
because some of those points still provoke in engineers something between admiration and nervous laughter.
There are documents you read and think, was this written by serious people? Or was someone checking whether the room was still awake? The specification for the Tu-160, early 1970s. Classified, of course. But the point isn't the classification. The point is what's written in it, point by point, with comments. Top speed, Mach 2.2, about 1,380 miles per hour. For a fighter, normal. For a machine with a takeoff weight of 600,000 pounds, it's like ordering a freight train to jump across a canyon. Physically possible, but every element of the structure takes loads under which the metal starts to live a life of its own. At that speed, the oncoming airflow heats the leading edges and the nose radome to 285 to 320 degrees Fahrenheit, 140 to 160 Celsius. For high-strength aluminum alloys, that's the critical zone. Aluminum starts losing strength exactly there, which means titanium in the most loaded assemblies. The central fuselage beam, 39 feet, 12 meters of titanium, the spine of the machine. It was welded in vacuum chambers. In open air, titanium spoils instantly during welding. That single part cost as much as several fighters. Had it cracked, the aircraft would have folded in half in the air. Fix that for now. It all comes together later. Range, around 7,500 miles without refueling. But here's a nuance that makes 15 hours in the Cocoon even more dramatic. Those 7,500 miles are at subsonic speed. If the Tu-160 goes supersonic, its range collapses catastrophically to roughly 1,200 to 1,550 miles. That is, for most of the route, it goes quiet and slow, saving fuel. Supersonic is a short dash at the necessary moment, which means the crew flies for hours in patrol mode and must stay combat capable right up to that dash. 15 hours. That's not a work shift. It's a day cut in half. A surgeon doesn't operate that long. Soviet long-range aviation had a rule. After a 12-hour flight, a crew was entitled to a minimum of 48 hours of full rest, an officially recognized off-the-scale load. And here, 4 men, a closed volume, and a task you cannot look away from. Payload, up to 99,000 pounds. That's 45 tons of missiles in 2 bays, each roughly the size of a small garage. Kh-55 cruise missiles, later the Kh-55SM. Each weighs about 3,300 pounds, with a launch range up to 1,550 miles. So the aircraft need not fly straight to the target. It must reach launch distance and do its work. Sounds logical, but here the system cracks. Because the Kh-55SM missiles were larger than their American counterpart, the AGM-86B, and heavier, the Kh-55SM weighs around 3,700 pounds, the AGM-86B around 3,200. 550 pounds of difference per missile. Multiply by 12 standard missiles in the bays, and you get more than 3 tons of extra weight in the payload alone. Which means larger weapons bays, a wider, longer fuselage. The aircraft grows. The mass grows. You need more thrust, more fuel, and the mass grows again. Engineers call this the design spiral, when each requirement drags the next tightening behind it. The spiral has no end. There's only a point where someone says, "Stop, this one flies." The Tupolev people found that point. but they paid for it. Now, the strangest point of the specification, the one that caused that long silence in the room. Crew, 4. Pilot, co-pilot, navigator, weapons systems officer, and living conditions ensuring the combat capability of the crew throughout the entire flight. Not acceptable conditions, not tolerable, precisely ensuring combat capability. That's a fundamentally different formulation. It's not, "You'll endure." It's, "You'll be ready to work after 15 hours exactly as after 1. Someone in the ministry understood what they were doing, or, on the contrary, didn't understand at all, and wrote it as self-evident. To this day, it's unknown which version is worse. Because fulfilling that point proved harder than building a supersonic airframe, what does combat capability after 15 hours mean? It's not a question of comfort, it's physiology. The human body in a closed space, under constant noise, vibration, and swings of pressure and oxygen, starts to degrade after roughly 8 hours. Not sharply, gradually. Reaction slows, concentration drops. Decisions come slightly slower, slightly less precisely. Slightly is a death sentence when the subject is a strategic missile carrier. By that point, the Americans had accumulated experience on the B-52, long patrols, airborne alert duty. They knew how it worked. They built life support systems not as an option, but as part of combat effectiveness. The Soviet school had almost none of that experience. The Tu-160 flew long, but its crews spent several days recovering after such flights. That was considered normal. Nobody asked, and what if there's no time to recover? Here's where the strange part begins. Because this very point, about combat capability, became the axis around which the whole story of the Tu-160's comfort turned. Not because someone decided to pamper the airmen, but because without it, the aircraft simply didn't do its job. The engineers dug into details they'd never thought about before. Cockpit lighting. It turns out it must change spectrum depending on the time of day outside. When you cross several time zones in a single flight, the crew's body clocks go astray. The seats, modified K-36s, the best ejection seats in the world at the time, but hard. To sit in them for 15 hours, special multi-layer ventilated cushions were developed. Without them, the pilot's skin literally burned from immobility. And the lavatory. A pressurized cabin at 50,000 feet. The air cleaning system must cope instantly. Any smell in a closed volume is already a factor that lowers that very combat capability. One of the designers who worked on the Tu-160 life support systems recalled, no name given, the source is indirect, that the first mock-up of the crew rest area looked roughly like a train compartment. 2 berths, a curtain, a fold-down table. The military representative looked, thought, and said something close to this. This isn't the Moscow-Kharkiv sleeper. A man has to rest in 2 hours, so he can then work 6 hours without mistakes. The compartment was redone. Then again, and again. We'll return later to what came of it. Because what came of it was unexpected. In both directions. There's a moment in the history of any large project when people stop arguing about whether it should be done and start arguing about how. At the Tupolev Bureau, that moment came in 1973. But the argument wasn't only internal. Tupolev had initially proposed his own shape for the machine, the 160M project, a tailless design resembling the Tu-144.
an aerodynamically clean aircraft. Beautiful. But on performance, it lost to the Myasishchev Bureau's M18. It lost fairly, by calculation. And then a decision came from above that still makes aviation historians smile. Tupolev was ordered to take the Myasishchev layout as his basis. Picture it. One of the most authoritative aircraft designers in the country, and he's told, here are someone else's drawings, refine them. That was the real clash of titans. Not abstract, but very concrete. Tupolev, a man of enormous pride, was forced to work with someone else's idea. What he thought of it isn't recorded in the documents. But those who worked nearby recalled, he smoked a great deal. The first argument, about the wing. Variable geometry wings aren't a Soviet invention. The Americans applied them on the F-111 back in the 1960s, then on the B-1. The idea is simple. At low speed, the wing spreads wide, more lift, shorter takeoff run. At high speed, the wing folds back, less drag, higher speed. It sounds like a perfect solution, but it has its price. The pivot of a variable geometry wing on a 600,000-pound aircraft isn't a hinge on a door. It's an assembly that, with each cycle of moving the wing, takes loads of hundreds of tons. It must work at temperatures from -76 Fahrenheit, -60 Celsius outside, to +320 on heated surfaces. It must never fail, because if it fails, the aircraft becomes uncontrollable. The veterans called this assembly, unofficially, the country's main frame. The whole aircraft was, in effect, built around this titanium part. To roll titanium plates thicker than 4 inches, the most powerful press in the world, with a force of 75,000 tons, was built in Samara, specially for this alone. Had a micro crack appeared in the beam, 600,000 pounds would have folded in the air like paper. One of the lead designers insisted the pivot must be made on a fundamentally different principle than on the B-1. There, a complex multi-element assembly. Here, more monolithic, simpler, more reliable. Another objected, mass, the design spiral again. They argued a long time. In the end, they did it their own way, and that assembly turned out to be one of the best in the world. But how much it all cost is a separate story. The second argument, about the engines. In 1973 to 74, an engine named the NK-32 didn't exist even on paper. The NK-25 for the Tu-22M3 was in development, powerful but different. It was from that one, developing the series, that the Kuznetsov Bureau would grow by the late 1970s what became the NK-32. But for now, only promises and calculations. 4 such engines were meant to give a combined thrust of 220,000 pounds on afterburner, more than any other combat aircraft in the world. And here's the first real dirt of reality. The aircraft was designed around an engine that didn't yet exist. Its characteristics were taken from Kuznetsov's calculations, and Kuznetsov took them from what he hoped to achieve. Promises are a fine thing, but not when the entire shape of the machine is laid down on them. One subcontractor engineer recalled, when the first real thrust measurements of the prototypes diverged from the calculated ones, not by much, by a few percent, everything had to be recalculated. The fuel system, the strength characteristics, The takeoff distance. A few percent. It seems a trifle. It wasn't. The third argument, and the longest, about where the crew sits. On the Tu-160, the cockpit was traditional, with large glazing, a wide field of view. Familiar, understandable. Pilots knew what to expect. On the Tu-160, the cockpit is different. An elongated nose, small side windows, limited view down and to the sides. This isn't an oversight. It's a consequence of supersonic aerodynamics. The shape of the nose is dictated by speed, not by the pilot's comfort. Test pilots brought in for the mock-up commissions reacted in different ways. Some said, "Fine, we'll get used to it." Others, bluntly, "It feels like flying inside a pipe." And here the engineers ran into a problem they hadn't expected. Two, in fact. The first, psychological. Closed space plus limited view plus 15 hours. A man in a pipe tires faster. They solved it through color. Instead of the standard emerald green fitted to the MiG-21 and the Tu-154, the Tu-160 cockpit used light, warm tones and a gray metallic to widen the space visually. A trifle? No. It's part of that same point about combat capability. The second, purely practical. Taxiing on the ground, Tu-160 pilots can't see the runway directly in front of them at all. The nose is too long. They navigate by side references, like drivers of a multi-trailer rig, on an aircraft of 600,000 pounds. And the third argument, about the control column. Every strategic bomber had huge yokes. Tradition, habit, the muscle memory of generations. On the Tu-160, they fitted a stick, a joystick, as on a fighter. The veterans were furious. How do you fly a 600,000-pound beast with one hand? The designers explained calmly. You need room for instrument panels and for the knees, critical during ejection. The veterans weren't appeased. The stick stayed. A solution was found. For now, fix this. The problems turned out to be where nobody expected. If you're new to this channel, subscribe. We don't do parade ground histories about Soviet might. We take apart how it actually was, with numbers, with arguments, with the dirt of reality. There are many such breakdowns still ahead. By the end of 1974, roughly then, the shape of the aircraft began to take form. Not because all the arguments had ended, because the time for arguments had ended. This is the Soviet logic of large projects. At some point, a signal comes from above. Enough discussion, start building. And they start. With an engine that doesn't yet exist. With a pivot that hasn't yet been proven. With a cockpit in which the pilots feel they're in a pipe. And, few know this, with a production process that turned out to be more dangerous than expected. When they began assembling the first airframes, it emerged that titanium shavings and dust could self-ignite during welding. The workshops became sites of extreme fire hazard. Workers worked in white, lint-free coveralls, as in an operating room, not for aesthetics, so that not a single speck fell into the vacuum weld. A plant assembling a strategic bomber worked in the regime of a surgical operation. Formally, everything was correct. There's an assignment. There are decisions. In practice,
Each of them carried a question whose answer would come only in testing. And the tests are a separate story. And it begins not where they thought. December 18th, 1981. Zhukovsky. The first flight of the Tu-160. The machine was rolled out onto the runway. The crew, under test pilot Boris Veremai, 4 men, commander, right-hand pilot, navigator, weapons systems officer, no flight engineer, his functions distributed between the crew and the automation. The aircraft took off, landed. Officially, everything nominal. Unofficially, that same day the Bureau began going through the flight recorder data, and there were several readings not spoken of in public. Then a few more. Then it turned out that one of the 4 engines had behaved not quite the way it should. Not a disaster, just not quite. In aviation, that's worse than a disaster, because a disaster is clear, and not quite is the beginning of a long story. The NK-32 is an outstanding engine. That's true, and it shouldn't be understated. 4 combustion chambers, a bypass layout, an afterburner, thrust-on afterburner around 55,000 pounds. Together, 4 engines drive a 600,000-pound machine to twice the speed of sound. That's physics at the edge of the possible. But the NK-32 had a problem that open sources wrote about carefully. The engine worked, but it worked with a temper. At certain settings, especially with sharp changes in thrust, vibrations arose in the engine. Not catastrophic, but persistent. The pylons on which the engines are mounted to the wing took those loads on themselves. So did the wing. And the wing on the Tu-160 already lives a complicated life. It changes its sweep angle. It carries loads and maneuvers. It works at temperatures that shift by tens of degrees in minutes. One mechanic of the technical crew recalled, after flights they inspected the weld zones of the central beam, the spine of the machine. Sometimes they found what the documents called microcracks. In conversation, they called it nothing at all. They looked in silence and passed it up the chain. And here's an important nuance many don't grasp. Steel, when it grows tired, warns you. It groans, it deforms. Titanium doesn't. It accumulates fatigue unnoticed and then fails instantly. Brittle failure isn't a crack that grows. It's when everything goes at once. Micro cracks in the welds of the central beam weren't simply a defect. They were a verdict on the whole technology. They had to develop annealing of the entire beam in a vacuum furnace. An enormous part, 39 feet of titanium, was placed in a furnace and held at high temperature without access to air. Only that way were the internal stresses in the welds relieved. Every beam. In a vacuum furnace, specially. Hold that in your head. Now, about the fuel. Because without it, the picture is incomplete. 326,000 pounds of jet fuel, a full load. That's not simply fuel. It's ballast that determines the entire behavior of the machine in the air. As fuel is used up, the aircraft's center of mass shifts. This happens on any aircraft, but on the Tu-160, the scale is different. The engineers solved this elegantly by pumping fuel between tanks, automatically depending on flight mode and remaining fuel. The Tu-160 fuel system is a separate computational task. 13 caisson tanks built directly into the airframe structure, a complex sequence of usage, a constant recalculation of the center of gravity. Sounds logical, but it means that if the fuel system automation fails, the center of gravity drifts. And an aircraft at supersonic speed with the wrong center of gravity isn't a technical failure. It's a verdict. In the documents about several fuel system incidents during the test period, silence. They preferred not to remember it. But people remember. Here's a figure best kept in mind. On a single sortie with a mixed profile, subsonic plus a short supersonic leg, the Tu-160 burns from 110 to 175,000 pounds of fuel. It depends on the flight profile, the load, the engine settings. 50 to 80 tons on a single sortie. An American family in the 1980s might burn a few hundred gallons of gasoline a year in the family car. The Tu-160 on a single combat sortie burned what dozens of such families spent in a year. This isn't a condemnation, it's simply scale. So you understand what's meant when someone says aircraft. But the most unexpected problem wasn't in the engines or the fuel. It was in the hydraulics. The Tu-160 is hydraulically controlled. A high-pressure system, 3,000 pounds per square inch, 210 atmospheres, the standard for heavy Soviet machines of the time. For comparison, the American B-1B ran 4,000 pounds per square inch. Soviet engineers deliberately held to the proven standard. More reliable. But it meant bulkier units and lines. Mass again. The wing sweep mechanism, the rudders, the flaps, all hydraulics. If the cylinders of the wing mechanism operate out of sync, the wing jams in an intermediate position. The aircraft becomes uncontrollable. Hydraulics love cleanliness. The smallest particles in the fluid, and the valves start to work with delays. Delays in the hydraulics of such a machine are seconds that decide everything. During the test period, leaks of hydraulic fluid were recorded regularly. Small ones, through seals, through the joints of the lines. Not catastrophic, but before inspections, they tried to fix them. Sometimes they didn't manage. Then, they wiped it down and didn't allow photographs. Formally, all within limits. In practice, worse ahead. All of this, engines with a temper, fuel automation, hydraulics, created a situation the engineers described in one word: load. Not on the metal, on the crew. Because all these systems required constant monitoring, not only automatic, human. The weapons officer and the right-hand pilot on a long flight ran the systems under a load comparable to a surgeon in the operating room. Only the operation lasts 15 hours. And at some moment, you might not notice. Here, the global question returns in full force. Was this an aircraft that demanded the impossible of men, or men who learned to make the impossible normal? There's no answer yet, but it's close. There are things the documents don't record at all. How the Tu-160 cockpit smells after 8 hours of flight. What happens to a man when beyond the window is the black abyss of the Atlantic, altitude 50,000 feet, minus 76 Fahrenheit outside, and no one for hundreds of miles around. What the commander feels when, at 4 in the morning Moscow time, and by local time it's anyone's guess, the zones went astray long ago, his eyelids begin to grow heavy. None of that is in the reports. In the reports, crew capable, no complaints regarding well-being. But people remember. Boris Veremai, commander of the first flight, chief test pilot of the Tu-160 in the program's early years, said in one interview, already in the 1990s, that the hardest part of long flights wasn't flying the aircraft. Flying is a profession. It's drilled. It's muscle memory. The hardest part was not letting the crew slip into standby mode. There's a state pilots enter on long flights. The body adjusts to monotony. Reactions slow. A man is formally awake, but in fact working at half strength. Vermeer said he deliberately staged small shake-ups, asked the navigators non-standard questions, requested they recheck the already checked, sometimes feigned mild concern about instrument readings that were perfectly normal. Professional deception, for the sake of safety. It's written in no flight operations manual. It's personal experience, passed from commander to commander. Now, about the rest area. The one redone 3 times. In the end, it came together. By Soviet standards, unexpectedly well thought out. 1 fold-down berth in the narrow passage behind the pilot's seats. The crew rests in turn while 3 work. You can stand at full height only in that corridor between the workstations and the rest module. A special variable firmness cushion, polyurethane foam developed specially. Under constant vibration, the body doesn't relax the way it does on the ground. A small galley. Electric warming of food in pouches. Coffee. This was fundamentally important. One pilot recalled that the smell of coffee in the cockpit 6 hours into a flight was the best way to switch the crew back on. And the toilet. A compact module with a stiff curtain, room enough literally to squeeze in and close it. But compared to the Tu-95, it was another world. At least there was a curtain. And its own air cleaning system. By the standards of strategic aviation, a revolution. By the standards of ordinary life, very modest. There was one comic incident that became a legend among the test crews. During one long test flight, the navigator went to the rest area to sleep, as scheduled. Lay down, fell asleep. After the allotted time, they woke him, and he came back out to his console, fully convinced that some 4 hours had passed. 40 minutes had passed. The navigator himself had switched the lighting when he went to rest, from combat red to ordinary white. Red light doesn't blind in darkness and helps those working keep their night vision. White is the domestic light for rest. He switched on white, and his body took it as a change of day. Then he returned to his station, red again. 2 transitions in 40 minutes. The body clock simply went mad. The navigator later said, "I didn't understand what time it was, at all. I knew only what the instruments showed." This sounds like a small curiosity. It's not a trifle. Because a man who doesn't understand what time it is also doesn't understand how long he's been awake. And that's already a question of combat capability. Now, fear. This is spoken of even more rarely than the toilet. One pilot, no name, speaking in a private conversation, admitted that on his first solo flights over the ocean in the Tu-160, he had one obsessive feeling. Not fear of death, that's different. Pilots get used to it or leave the profession. Something else. A feeling of the scale of the mismatch. That you, a man 40 years old, family in Pryluky, fond of soccer and fried potatoes, sit in a seat and behind your back hangs a weapon that can change history.
Not metaphorically. Literally. "I tried not to think about it," he said. "Because if you start thinking, you're no longer flying. You're just sitting and thinking." This isn't weakness. It's honesty that doesn't exist in official reports. None of it is in the documents. At all. But it was these men who flew. And they flew well. Subscribe. If you've read this far, then you're interested not in the parade ground story, but in the living one. Ahead is the hardest part. What happened when the system cracked? And what the system did afterward. About the crew, one last thing. 4 men in a closed volume for 15 hours aren't simply a professional crew. It's a small society with its own hierarchy, its habits, its tensions. Someone snores in the rest area. Someone can't stand the smell of another's food. Someone grows irritable by the 10th hour. The commanders knew this. Selecting crews for long flights was a separate task, done not by psychologists on paper, but by commanders from experience. Who flies calmly with whom? Who helps rather than hinders in a tense moment? Next, what happened when all that tension reached the point after which the system could no longer pretend everything was fine? 1992. Pryluky. Ukraine is already a separate state. The Soviet Union has been gone 8 months. 19 Tu-160s stand at the airfield, the largest concentration of these machines outside Russia. They belong, formally, to Ukraine. They're serviced, by inertia, by the same personnel who serviced them a year earlier, under a different flag. And here begins a story that isn't technically a disaster, but in its consequences, worse. The Tu-160 isn't simply an aircraft, it's an ecosystem. The machine requires specific spare parts, produced at plants in Kazan, Samara, Moscow. It requires specific fuel, aviation kerosene of special grades with additives. It requires specially trained technicians who know this particular machine. All of this, in 1992, began to fall apart. Spare part deliveries from Russia stopped. Not at once, not by order, simply the supply chains, which had held on the Soviet logic of everything is shared, became interstate overnight. The plant in Kazan was now in another country. The documentation, partly classified, partly simply not handed over anywhere. The technicians kept working, from what there was. Craftsmen in uniform, they were called in the crews. Only now it wasn't ingenuity. It was the necessity of survival. Here's what happened to the aircraft. Hydraulic seals, a consumable, replaced regularly. The stocks lasted about a year. Then came replacements deviating from the regulations. Not the right fluid grades, not the right seals. Leaks became the norm. The NK-32 engines required scheduled servicing, strictly by operating hours. The Ukrainian side had the documentation, but not in full, not with all the up-to-date modification bulletins. Some had simply not been handed over. Kerosene, by the way, Ukraine could produce. Its oil refining was powerful. The problem wasn't in the fuel itself. The problem was in the money. 175,000 pounds of fuel per sortie. 19 machines. And in the politics. Strategic aviation with nuclear weapons aboard didn't fly, not because there was nothing to fuel it with, but because there was no one to give the orders, and no one to take responsibility. On one machine in 1992, a routine inspection found a micro crack in the engine pylon attachment zone. Not critical, by the criteria of Soviet documentation,
But that documentation was written for conditions where the next inspection would come at the prescribed interval, not who knows when. The machine was grounded, formally, for modification. In fact, no one knew what to do with it. That decision would come back around, but not the way it might have. But the most painful crisis wasn't technical. It was human. The Tu-160 crews in Pryluky had sworn an oath to the Soviet Union. Now they were offered an oath to Ukraine. Some officers refused and left for Russia, with their families, their belongings, their personal files. Some stayed, not always from conviction, sometimes simply because there was nowhere to go, the children in school, the wife with a job. And these men, some of whom took the Ukrainian oath, some who carried on without any oath at all, kept servicing the aircraft, professionally, carefully, because it was their machine. They knew it. They loved it, if you can speak that way of military hardware. One technician who stayed in Pryluky into the mid-1990s recalled, "We didn't think about whose aircraft they were. We thought, our aircraft, and we looked after them." None of that is in the documents. In the documents, diplomatic negotiations, transfer acts, protocols. There's a question that takes us back to the beginning. This aircraft, an engineering feat, or a costly mistake of a system that collapsed before the machine could serve out its time? Look, by 1991, 35 aircraft had been built, including prototypes and test airframes. 19 series machines of the 184th Guards Regiment ended up in Pryluky. The rest, at the plant in Kazan or in Zhukovsky, that is, on Russian territory. More than half the series fleet abroad. The country that created them lost them in a single collapse. This isn't a disaster in the air. It's something else. What exactly? In the next part. And one last thing about 1992. Those 19 machines in Pryluky, they stood, almost never flew. Sometimes they ran up the engines on the ground, sometimes performed short flights to keep the crew's skills, but mostly they stood, white, enormous, on a Ukrainian airfield. The technicians wiped the dust off them, checked the tire pressure, did what they knew how to do, because nothing else remained. White swans in Pryluky. Someone among the local residents recalled that when they took off, rarely, but they did, the whole settlement came out to watch. Not from patriotism, simply beautiful and frightening, and unclear what to do with it now. The system found it unclear too. That became apparent later. The resolution stretched over several years. Ukraine adopted non-nuclear status, and the strategic bombers became a burden. Keeping them was prohibitively expensive. The flights alone, 175,000 pounds of kerosene per sortie, multiplied by 19 machines. There was no money, and no political sense in keeping them. 10 machines were scrapped, cut up right on the airfield, on American money under the Nunn-Lugar program, Cooperative Threat Reduction. A beautiful name for the process of destroying something on which billions had been spent. 8 machines were saved by something else. In 1999, they were transferred to Russia against a gas debt, $285 million. The gas debt turned out to be what preserved the white swans for the Russian aerospace forces. They're still in service, some modernized to the Tu-160M standard. And one aircraft, tail number 26, remained in Ukraine, intact. Today, it stands in the Poltava Museum of Long-Range Aviation. And here's the most uncomfortable question of this story. If the Soviet Union hadn't collapsed, these aircraft would have flown for decades more, perhaps become exactly what they were meant to be, or perhaps been written off earlier, replaced by something new. No way to know. History has no subjunctive mood, only white aircraft on gray concrete, and technicians who wiped the dust off them, because nothing else remained. 1993. Pryluky. The technical staff of the 184th Regiment. There are almost no flights. Pay is delayed by a month, sometimes 2. Spare parts don't arrive. But the aircraft must be serviced, because if they aren't, they degrade faster than the political crisis can end. And men worked, without orders from above, without understanding why, simply because these were their aircraft. This isn't heroism, it's professional inertia, which in this case turned out to be stronger than everything else. Concretely, what they did. Hydraulic seals. The standard ones ran out. Finding a civilian analog was physically impossible. These aren't rubber rings from a hardware store. They're precision items of special fluoroelastomers that work at 3,000 psi in an aggressive fluid. No civilian plant in Ukraine produced anything like it. They found another way. They began removing live assemblies from machines that no longer flew, from donors. From the airframes standing on the far apron with minor technical problems. First, one part at a time, then several. Gradually, some machines turned into skeletons so that others could live. In aviation, this is called cannibalization, and it was the main tragedy of Pryluky. Not the lack of money, not the political crisis. The fact that the aircraft were slowly eating one another. Engine oil. The NK-32 runs on synthetic IPM-10 oil, not produced in Ukraine, and the stocks were critical. To replace it with something close in viscosity would have meant a turbine failure within a few hours. They found another way. Old oil was filtered and separated many times over to be reused. A gross violation of the regulations, but it worked. The navigation system. Inertial navigation requires alignment on precise geodetic points of the airfield. Otherwise, the gyroscopes sour, lose accuracy. In Pryluky, those points were known. The navigators regularly ran the gyros right on the aprons, without flying, just to keep the systems from degrading. This was one of the few technical actions that could be done entirely correctly. And they did it. The documentation was written after the fact. Acts were signed, sometimes without reading, because there was no time to read, and the act was needed now. One of the senior technicians who worked in Pryluky in that period described those years roughly like this, paraphrased. We understood we were doing something not quite right, but the alternative was to abandon the machines completely, and we couldn't abandon them. This isn't a justification, it's a diagnosis. The system that created these aircraft didn't foresee a situation where they'd be cut off from the production base. Not because the engineers were bad, because the system didn't know how to plan its own collapse. And here, if we answer the global question honestly, is the main problem not technical, systemic. Now, about what was happening in Russia in parallel. The Russian Tu-160s, those that remained at the Kazan plant and a few in Engels, were also going through hard times. The 1990s for the whole defense industry were a time when the word funding was spoken with roughly the same intonation used for something unattainable. The Kazan plant switched to survival. Production of new machines all but stopped. Some specialists left, some for business, some simply for another life. Those who stayed held on through enthusiasm and the Soviet habit of working regardless of pay. For comparison, the American B-1B in those same 1990s went through several planned modernization programs: new avionics, new self-defense systems, an expanded weapons list. The money was found because the system hadn't collapsed. The Soviet Tu-160 in the 1990s stood, literally. One moment few know about. In 1995 to 1997, Russia offered $2 billion for all 19 machines. Ukraine, under pressure from Western partners and its own political ambitions, asked for $8 billion for aircraft that stood and degraded. For the Russia of the 1990s, that was a sum from another reality. It was precisely this price deadlock that started the scrapping. They cut up machines and bargained in parallel. When the knife reached the last airframes, they came to terms, not on a market price, on the gas debt. $285 million. 8 machines flew to Engels in 1999. That, perhaps, is the best assessment of what the craftsman in uniform in Pryluky did all that time. There's one more detail about that flight. The Ukrainian side fueled the machines to the brim with their own kerosene, although Ukraine itself was catastrophically short of it. The technicians wanted their Swans to make it without trouble. And when the Russian engineers received the airframes in Engels, they found that in some cockpits, the factory covers were still on the headrests. Perfect cleanliness. The machines had stood for years, degraded, been taken apart for parts, and yet the seats had been wiped down. People did what they knew how to do, to the end. But the story doesn't end there, because when the machines flew over, something important became clear. Some of the modifications made on the Ukrainian aircraft, deviating from the regulations, actually worked. The technicians had found solutions no worse than the standard ones, just different. This doesn't mean it should be done that way. It means that people who know their machine sometimes know it better than the manual. Next, what this actually meant. Not for the aircraft, for everything. 1999. 8 machines flew to Engels. This was the end of one story and the beginning of another. But between them, a pause that holds everything that matters most. Because when the Russian engineers began receiving the airframes, they ran up against not a technical question, they ran up against a question of meaning. What do you do with aircraft that have stood almost 10 years, that were built for one country, that country is gone, the aircraft belonged to another, which has also changed beyond recognition? For what war were they made? And is that war relevant now? There was no answer in 1999. There was only a choice: write off or restore. They chose to restore. That decision seems obvious now. In hindsight, everything seems obvious. But at the time, it wasn't obvious at all. Because the Tu-160 of the late 1980s is an aircraft with a digital architecture on a heavy Soviet component base. The Obzor K targeting navigation complex, The Orbita 20 onboard digital computer. The brains were digital. But the hardware they ran on was enormous, power-hungry, and temperamental. Suitcase-sized modules, where today there's a palm-sized board. By the late 1990s, part of that base was morally obsolete. For comparison, the American B-1B by that time had gone through several waves of avionics modernization. But here a nuance matters. Under the START treaties, the B-1B was stripped of the ability to carry nuclear weapons. It was reoriented to conventional munitions for local conflicts. Hence the investment in electronics for precision bombing in Iraq and Yugoslavia. The Tu-160 kept its status as a nuclear missile carrier. Precisely for that reason, the Soviet, then Russian, side preserved not the electronics, but the airframe platform, one of the best in the world. That was good for 1985. For 1999, already a question. And here, an unexpected fact that overturns the whole picture. Precisely in the late 1990s and early 2000s, it emerged that the Tu-160 airframe, for all the problems with avionics and servicing, was outstanding, better than initially assumed. The airframe's service life proved greater than calculated. The titanium beam, the very one welded in vacuum chambers and annealed in vacuum furnaces, held loads better than laid down in the specifications. The variable geometry wing worked reliably. This meant one thing: the aircraft could be modernized. Not build a new one, modernize the existing one. Fit new avionics, expand the weapons range, improve navigation. The airframe would take it. So began the road to the Tu-160M. In 2018, the Pyotr Denikin took to the air, a machine completed from Soviet groundwork. And in January 2022, the first Tu-160M built entirely from scratch, from new titanium sheets on restored production. This is a critical point, proof that the technology is alive. The 75,000-ton press in Samara works. The ELU-24 vacuum chamber in Kazan for welding the beams, the size of a two-story house, has been restored. When they took it up again in the 2000s, it turned out some assemblies were unique and couldn't be ordered abroad. They had to restore the Soviet drawings. This bears on the question of the monument to a system. Sometimes monuments come back to life. The craftsmen in uniform, who for 7 years washed the seats and ran the gyros on the apron, they, without knowing it, preserved airframes that had a service life for another half-century. But here's a question deliberately held back. What was all of it for? The Tu-160 was created for a war that didn't happen. The Cold War ended exactly at the moment the aircraft was ready. The missiles it carried never flew to targets. Patrols over the Atlantic there were, but not combat ones, demonstrative ones. So it works out. 20 years of development, billions of rubles, tens of thousands of people, all so the aircraft could stand in Pryluky, then be partly cut up, partly fly to Engels, and become the basis for a next-generation machine? Funny? No. Tragic? Also not quite. Because it was this very aircraft, with all its problems, with the whole story of Pryluky, with the whole logic of the Cold War, that became the point from which something important grew. Not military, technological.
Everything mastered in creating the Tu-160, vacuum welding of titanium, the 75,000-ton press in Samara, the fuel management system across 13 caissons, the technology of annealing a whole beam, didn't vanish with the USSR. It remained. That same press in Samara was later used to produce titanium items for the nuclear industry and aerospace. The technologies of vacuum welding of large titanium structures are today applied in submarine construction and in the aerospace sector. The methods of calculating fuel systems with active center of gravity management are the basis of modern systems on civilian airliners. This doesn't mean the Tu-160 was built for the sake of civilian technology. It was built for war. It's simply how big engineering works. The technological groundwork doesn't die with the political order. It remains in people and in machine tools. That's the moment of truth. Not victory and not defeat. Simply, what exactly remained? If you've read this far, then you're interested not in the pretty story, but in the real one. Subscribe. Ahead are the final parts, where we put it all together, and where I finally answer the main question. Ahead, worse in terms of simple answers, but better in terms of understanding. Because in the next part, we look at the numbers, honestly, without triumphant fanfare and without self-flagellation. Simply, what it cost, and what could have been done for the same money. The answer there will be unexpected, but fair. Let's speak honestly, without triumphant fanfare and without self-flagellation. One Tu-160 by the late 1980s and early 1990s cost, by various estimates, from 250 to 300 million Soviet rubles. For comparison, a Project 949A nuclear submarine, the anti-type, the Kursk type, cost around 230 million. One aircraft was more expensive than an enormous nuclear submarine cruiser. This isn't an exaggeration. It's the Soviet estimate. But here's what's known for certain. 1 hour of Tu-160 flight cost as much as the annual salary of roughly 10 military technicians. And the machine flew 15 hours. Multiply. For the money of a single Tu-160 combat sortie in Soviet times, you could have built several dozen apartments in a standard 5-story block somewhere in Kharkiv or Voronezh. This isn't a metaphor. It's a proportion. Hold that in your head. It's not an accusation. It's context. Now, the debunking of a myth. It's accepted that the Tu-160 is an unqualified masterpiece of Soviet engineering. The peak, the limit of the possible, the best that was made. That's true, but not the whole truth, because behind that truth hides another. The Tu-160 was built 35 times. Only 35. For comparison, American B-52s were built 744 units. B-1Bs, 100. Series production isn't only money. It's also the reason a combat aircraft exists at all. It must be in sufficient numbers to affect the balance of forces. 35 machines is a demonstration of capability. It isn't a fleet. The Soviet system knew how to make unique things, sometimes in a single copy, sometimes in 35. But it struggled to make them in 744. Here's the author's assessment. Plainly, without reservations, the Tu-160 is neither a masterpiece nor a mistake. It's a symptom aircraft. not a disease, but an exact indicator of what was happening inside the system that created it. The system knew how to mobilize for the impossible. To weld a beam in a vacuum chamber, it could. To create an engine with 55,000 pounds of thrust, it could. To make hundreds of thousands of people work for a result, it could. But the system didn't know how to maintain what it created, didn't know how to plan a life cycle, didn't know how to provide logistics in peacetime. And it had no idea at all how to plan its own collapse. That's why the best machines in the world stood in Pryluky and slowly ate one another. Not because they were bad, because the system that bore them departed before they did. Now, the answer to the global question, the one standing since the first part. Is the Tu-160 a monument to engineering genius, or a monument to a system that spent money as if it were being printed in the shop next door? Here's my answer. They're the same thing. Genius and prodigality here are inseparable. Without the prodigality, there'd be no genius, because it was precisely the boundless resource that let engineers solve tasks that in market logic simply made no sense. A 75,000-ton press for a single part of a single aircraft. In a market economy, that's impossible. In the Soviet one, it happened. But without the genius, the prodigality wouldn't have become history. Simply spent money, no one remembers it. But this aircraft, people remember. It was a feat. And at the same time, a mistake. Because one doesn't cancel the other. That's the honest answer. Not pretty, but honest. And one last thing about numbers. Of the 35 machines built, today around 16 are in flying condition in the Russian aerospace forces. Some are undergoing modernization. New ones are being built, slowly, but built. American B-52s, which began flying 29 years earlier than the Tu-160 in 1952, number 76 still in service. And they'll fly into the 2050s. 29 years of difference. The veteran machine outlives the giant machine in numbers and in service life. This isn't a comparison in anyone's favor. It's simply different approaches to what building an aircraft means. There's one more figure worth naming. The Tu-160 program in total, development, building the production base, series production, operation, cost, by various estimates, a sum comparable to building several large city districts. Not individual houses, districts, with schools, hospitals, roads. This doesn't mean districts should have been built instead of aircraft. A state that has no strategic deterrent will keep neither districts nor schools. That's the system's argument. And it's not without logic. But that, for this money, the country got 35 aircraft, half of which were later cut up, that's also a fact. Simply hold both facts side by side. Don't choose between them. Both are true. Next, an alternative history. What would have been if the money had been spent differently? Spoiler, there was no good way out. Not one. Picture a meeting. Moscow, early 1970s. At the table, the military, the designers, the planners. On the agenda, one question. How to answer the American B-1. And someone, not the chief, someone from the second row, raises a hand and says,
And maybe we don't need supersonic? A pause. Maybe, instead of one Tu-160, 10 improved Tu-95s. Cheaper, simpler, more targets, more experienced crews. He wasn't answered rudely. He simply wasn't answered. Because the system didn't work that way. Better, faster, higher wasn't up for discussion. It was the condition of existence. But the question was the right one, and it's still not closed. Option A. Instead of the Tu-160, a mass-produced Tu-95MS. By the mid-1980s, the Tu-95MS, with Kh-55 cruise missiles, was already flying. A good machine, but with one fundamental limitation. The Tu-95 means high altitude and subsonic speed. American missile systems and carrier aviation by the 1970s already considered it a comparatively vulnerable target. The Tu-160 was conceived differently, as multi-mode. A breakthrough at low altitude with terrain following, where radars barely see it. Supersonic, only for a quick exit from the danger zone. That's a fundamentally different tactic, not simply faster. And one more detail about the missiles. The Tu-95MS carries 6 Kh-55 on an internal rotary launcher. To take more, external pylons are needed, which sharply reduce its already modest speed and range. The Tu-160 carries 12 missiles internally, without loss of performance. As a truck for nuclear weapons, it's nearly twice as effective. If the money of the Tu-160 program had gone to the Tu-95MS, the fleet would have been larger. But each airframe more vulnerable and less flexible tactically. Sounds logical, but it's a trap, because this option has a hidden cost. The hidden cost of option A, a technological dead end. If you don't build the Tu-160, you don't need the 75,000-ton press. You don't need the ELU-24 vacuum chamber. You don't need the technology of welding large titanium structures. 20 years later, when something fundamentally new is needed, those competencies are gone. They can't be bought. They can only be built up through a real project. That's precisely why, in the 2000s and 10s, when they decided to restore Tu-160M production, it turned out the base exists. Hard, expensive, the drawings need restoring, but the base exists. Had the Tu-160 not been built, there would have been nothing. This bears on the question of whether the program can be called pure waste. Option B. Instead of the Tu-160, a bet on stealth. In the 1970s, the Americans were already working on what became the B-2 Spirit, a stealth bomber. Soviet intelligence knew of it, in general terms. What if the USSR had chosen an asymmetric answer? Not speed, but low observability. Theoretically, logical. An aircraft a radar doesn't see need not be made supersonic. It simply passes unnoticed. In practice, Soviet microelectronics in the 1970s was fundamentally incapable of creating the control systems stealth technology requires. The B-2 is first of all computing power and composite materials. But here's an irony that leaves a bitter taste. The mathematical foundations of stealth technology, the theory of the diffraction of radio waves on edges, were described by the Soviet physicist Pyotr Ufintsev back in 1962. In the USSR, his work was deemed a theoretical amusement with no practical application. In the USA, on its basis, they created the F-117, the first series stealth aircraft. That is, the mathematics was theirs, but the computers and materials to realize it were not. This is the systemic tragedy in concentrated form. They knew how. They couldn't do it. So option B was theoretically correct and practically impossible. Not because the designers were bad, because the system left no options. Here's the paradox. The technically correct choice was politically and industrially impossible, and the politically possible one was technically a gamble. And that's precisely why they built the Tu-160. Here's a question I want to leave open, and I want to hear your answer. If you'd sat at that meeting in the early 1970s and knew everything we now know about the collapse of the USSR, about Pryluky, about the gas debt, and the ELU-24, what choice would you have made? Option A, mass Tu-95MS, without a technological breakthrough, but with a real fleet. Option B, stealth, impossible with Soviet microelectronics. Option C, the Tu-160, 35 machines, half later cut up, but the technology remained. Write in the comments. This isn't a rhetorical question. There was no right answer there, and there's none here either. But that's exactly why it's interesting. The final feeling I want to leave. There was no good way out. Not one. The system that created the Tu-160 was built so that any choice had an unacceptable price. This isn't a justification of specific decisions. It's a description of the logic in which those decisions were made. Sometimes the most honest thing you can say about history is, they did what they could, in conditions they didn't choose. Next, the finale, where the machines stand now, and what to do with all of it. Engels, Saratov region, a long-range aviation airbase. If you go there on a clear day and stand at the perimeter, you can see them from afar. White, enormous. Against the gray concrete and the steppe sky, they look not like military hardware. They look like architecture. One journalist who visited in the 2000s wrote, "You stand beside it, and you can't believe it flies." I understand that feeling, because on the ground, the Tu-160 gives the impression of something static, a monument, an obelisk. And only when it begins its takeoff run and 4 NK-32s go to afterburner and the ground literally shakes underfoot, you understand that it's alive. This isn't a metaphor, it's physics. Where you can see a Tu-160 today, in Engels, in service, but you can't simply get there. In Poltava, tail number 26 red, the only Tu-160 in the world that any civilian can officially visit. They say the technicians there look after it with the same care as in Pryluky. Wipe it down. Check it. Only the engines are disabled, the equipment removed. This is no longer an aircraft in the full sense. It's a shell, a ghost, a body without a heart. A perfect image for the finale of this story. In Kazan, at the Tupolev plant, production of the Tu-160M is underway. Not a museum exhibit, living production. But to launch it, competencies had to be gathered, literally grain by grain, from those same elderly engineers who still remembered how it was done. The ELU-24 installations were modernized. The technology of electron beam welding and vacuum annealing was restored from scratch. The first airframe, built entirely from new materials, took to the air in January 2022. It was given a name, Valentina Tereshkova. The names of these machines aren't bureaucracy. They're part of their soul. The story hasn't ended. There's something special in standing beside a machine that has survived everything we've spoken of across 12 parts. Tail number 26 red in Poltava. White. Quiet. On the ground. Wingspan 180 feet in the spread position. You stand beside it, and you understand. There it is. Somewhere inside, that same fold-down berth on which the navigator slept 40 minutes and thought 4 hours had passed. That same little cabin with the stiff curtain, those same seats with ventilated cushions. All of it is inside. Only the engines can no longer be started. The equipment removed. The machine, a body. A shell in which there was once a heart. Outside, the same white paint, protection from the light flash of a nuclear blast, beauty as a side effect of the physics of survival. Now, simply beauty. Touch it with your hand and think. This is what people did. This is what they could do. I want to say something personal, not as a technical journalist, as a human being. I've worked for many years with materials on Soviet aviation, read the acts, listened to the people who built these machines and flew them. And here's what I understood. The Tu-160 isn't simply a weapon. It's a monument to an era when, for the sake of speed and beauty, no money was spared. When an engineer could receive an assignment that, by all the laws of physics and economics, was impossible, and find a solution. When the state, for all its absurdity and prodigality, knew how to mobilize the best people for the best they could do. It was expensive. It was inefficient. It left behind empty aprons in Pryluky and cut-up airframes. And it left behind the ELU-24 in Kazan, the 75,000-ton press in Samara, and living people, already elderly, some already gone, who remember how it was. How kerosene smelled at dawn, how the ground shook at afterburner, how the navigator came back from the rest area and didn't understand what time it was. That's also history. Not the parade ground kind, the living kind. Now, the final answer to the main question. Is the Tu-160 a monument to engineering genius, or a monument to a system that spent money as if it were being printed in the shop next door? Here's my final answer after 12 parts. It's a monument to people, not to the system. People within a system can be better than the system. Not to genius in the abstract, to the genius of specific engineers, specific airmen, specific technicians in Pryluky who for 7 years washed the seats and ran the gyros, not knowing why. The system created the conditions, good and bad at once. The people did what they could, and often more than they should have. That's the truth about the Tu-160. Not victory and not defeat. Simply, people did their work well, and the machine turned out beautiful. That means something too. If you have personal memories of this machine, you flew to Engels or Pryluky, saw it take off, heard of it from your father or grandfather, or served in long-range aviation yourself, right. Living history is worth more than any archive.
Every such story is a piece of the truth that's in no official document. And subscribe. Ahead are many more such breakdowns, without parade speeches, only what actually was. About people who did the impossible, and about systems that hindered and helped them at the same time. The Tu-160, the White Swan. A more beautiful name for a combat aircraft is hard to imagine, because a swan is a bird that's beautiful in flight, and on the ground, it almost goes unnoticed.